Hello, with this video we begin our unit on chemical bonding based on Chapter 6 in the textbook. Let's begin with an outline of the unit. In Chapter 6.1 we'll talk about an introduction to chemical bonding. We'll ask the question what types of chemical bonds exist, how are they formed, and how do we classify them. That's the topic of today's video. Then we're going to jump ahead to Chapter 6.3 and talk about ionic bonding. We're going to ask the question how are ionic compounds formed, and we're going to cover the concept of the formula unit, which is very important. In Chapter 6.4, we will talk briefly about metallic bonding, that is, how do metal atoms bond to one another, and we'll talk about how that model for metallic bonding explains properties of metals. In Chapter 6.2, we will talk about covalent bonding molecular compounds. How are they formed? What are their characteristics? And we will learn how to draw Lewis structures or electron draught structures to represent these compounds. And finally, in Chapter 6.5, we will talk about molecular geometry, that is, how we predict the three-dimensional structure of molecules and how the structure influences the properties. So let's begin with an introduction to chemical bonding. What is a chemical bond and why do atoms form them? Well, the definition is a chemical bond is a mutual electrostatic attraction between the nuclei and valence electrons of different atoms that binds the atoms together. And atoms form chemical bonds for one reason only, and that is to lower the potential energy of the system. There are two limiting types of chemical bonding, meaning they exist at the extremes of a spectrum. One type is ionic bonding, which involves an electrostatic attraction among large numbers of cations and anions, which we learned about in the previous unit. At the other end of the spectrum is covalent bonding, which involves sharing of pairs of valence electrons between two atoms. So let's look at these individually. In ionic bonding, many atoms of element A combine with many atoms of element B, and in the process, the A atoms transfer one or more electrons to the B atoms. In doing so, the A atoms acquire a positive charge, and the B atoms acquire a negative charge. Notice that this occurs not simply between one atom of A and one atom of B, but between large numbers of these atoms. So we can ask the question, what type of element is A? Well, we learned in the previous unit that metals tend to give away electrons to form cations, so A must be a metal. What type of element is B? Well, we also learned in the previous unit that nonmetallic elements gain electrons to form anions, so B must be nonmetallic. And as you can see, in the resulting ionic compound, there are large numbers of cations and anions packed together in what is called the crystal lattice, which we'll talk about in the next video. In covalent bonding, in contrast, a pair of atoms, in this case atoms C and D, come together and share a pair of electrons. Which electrons do they share? Why, the valence electrons, of course. Now, let's talk about two types of covalent bonds. Here is a diagram that shows two carbon atoms bonded to each other. The pale blue shading represents the electron clouds surrounding the pair of carbon atoms. As you can see, the two carbon atoms are sharing the pair of electrons equally, so we will call this a nonpolar covalent bond. Okay? On the other hand, in a bond between oxygen and hydrogen, we can see that the electrons are not shared equally. The blue shading indicates that there is a buildup of electron density around the oxygen atom and a deficiency of electron density around the hydrogen atom. That results in a partial negative charge on the oxygen atom and a partial positive charge on the hydrogen atom, indicated by the lowercase Greek delta. That little squiggly thing is little d in the Greek alphabet. Delta plus means the hydrogen has a partial positive charge. Delta minus means the oxygen has a partial negative charge. And we call this a polar covalent bond because electrons are shared unequally, so there is separation of charge. We observe that in covalent bonds, some atoms have a greater tendency to attract shared electrons toward themselves than others. In this case, we can clearly see oxygen has a greater tendency to attract the shared electrons. It's greedier for electrons. Okay? We can actually quantify that and assign and call the property electronegativity. Electronegativity is defined as the measure of the tendency of an atom in a bond to attract shared electron density toward itself. In this previous example, since oxygen attracts the shared electrons more strongly than hydrogen does, we would say that oxygen is more electronegative than hydrogen, or it has a greater electronegativity. And the more electronegative atom in a bond is assigned a partial negative charge, delta minus, because there is a buildup of electron density around that atom. So the question is there a quantitative scale of electronegativity? In fact, there is. It was devised by the American physical chemist Linus Pauling in the early part of the 20th century, and here is a section of the periodic table that shows elements with their electronegativity values in each box. The electronegativity values are not unit bearing, they are simply numbers, and we can see that there are actually some trends in electronegativities. So pause the video for a minute, look at the values, and see if you can see how electronegativities vary based on position in the periodic table. Well, clearly fluorine is the most electronegative element in the upper right-hand corner, and francium and cesium are the least electronegative elements in the lower left-hand corner. So the trends clearly are that the electronegativity increases as you go from left to right in the periodic table, and electronegativity also increases as you go from bottom to top on the periodic table. So, how can we predict the type of bond formed between two elements? Here's the idea. I give you a pair of elements on the periodic table, and I ask you to tell me what type of bond they form. So the first question is, will they form a covalent bond or an ionic bond? And the second question is, if it's a covalent bond, will it be a polar covalent bond or a non-polar covalent bond? Now, here's what the textbook says. You simply look up the electronegativity values for the two elements, which, by the way, you don't need to memorize. You will always have a table of electronegativity values, and you subtract the smaller one from the larger one and calculate what's called the electronegativity difference, symbolized by delta En. And according to the book, if the electronegativity difference is small, between 0 and 0.3, you'll say it's a nonpolar covalent bond. On the other hand, if the electronegativity is medium, between 0.3 and 1.7, you'll say it's a polar covalent bond. And if the electronegativity difference is large, 1.7 to 3.3, you'll call that an ionic bond. Unfortunately, this is not correct, and I can show you examples where this system fails. Let's consider hydrogen and fluorine. If I look up the electronegativity values, fluorine has an electronegativity of 4.0, hydrogen 2.1. That's a difference of 1.9. The book would predict that the hydrogen-fluorine bond is ionic, but that's incorrect. We know the hydrogen-fluorine bond is covalent. It's highly polar, but it's still a shared pair of electrons. Here's another example. Magnesium and iodine. If we look up the electronegativity differences, iodine is 2.5, magnesium is 1.2. That's a difference of 1.3. That would predict a polar covalent bond. But we know that the magnesium-iodine bond is ionic. It consists of magnesium cations and iodide anions. So clearly, this simplistic method of just subtracting the electronegativity values leads to incorrect conclusions. Here is a more accurate way to classify bonds, and I've given you a handout that describes this in detail. The primary criterion for classifying a bond is the type of elements that are involved. And in this class, if the bond is between a metal and a nonmetal, we're going to say it's an ionic bond. That makes perfect sense. We know metals like to lose electrons to become cations. We know nonmetals like to gain electrons to become anions. If you've got cations and anions, you've got ionic bonding. If it's a bond between two nonmetallic elements, we're going to say it's a covalent bond. Okay? Once we've determined that it's covalent, then we will use electronegativity differences to determine whether it's polar covalent or nonpolar covalent. So for example, if the electronegativity difference is less than about 0.4, we'll call it a nonpolar covalent bond. If it's greater than 0.4, we'll call it a polar covalent bond. If it's exactly 0.4, then it's kind of borderline. I would call it weakly polar. We can also determine that if we're comparing two different covalent bonds, the one that has the greater difference in electronegativity will be more polar because there is a greater disparity in electron attracting ability, therefore a greater separation of charge. Metalloids behave as nonmetals. And which atom in a polar covalent bond has the partial negative charge? Well, that obviously would be the more electronegative atom. So let's do some examples of classifying bonds. I'm going to give you pairs of elements, and we're going to classify each bond as ionic, polar covalent, or nonpolar covalent. And we'll explain why. Here's the first example, magnesium and nitrogen. Well, I find them on the periodic table. I see magnesium as a metal, nitrogen as a nonmetal, so I'm going to say that this is an ionic bond. Very straightforward. In the second example, silicon and bromine. Well, silicon is a metalloid, a nonmetallic element. Bromine is a nonmetal. So because I have two nonmetallic elements, I'm going to begin by saying that this is a covalent bond. Okay? But in order to determine whether it's polar or nonpolar, I'm going to need to calculate the electronegativity difference. So delta En, I'm going to subtract the smaller electronegativity from the bigger one. Bromine has an electronegativity value of 2.8. Silicon has an electronegativity value of 1.8. That's a difference of 1.0. That's a pretty moderate difference, so I'm going to call that a polar covalent bond. And in my final example, I'm going to look at the bond formed between boron and hydrogen. Boron is a metalloid, hydrogen is a nonmetal. So again, we have two nonmetallic elements, so I'm going to broadly classify this as a covalent bond. And then to determine whether it's polar or nonpolar, again, I'll calculate the electronegativity difference. Delta En, hydrogen has an electronegativity of 2.1, boron has an electronegativity of 2.0, so the difference is only 0.1, which is a small electronegativity difference. Therefore, I will classify this as a nonpolar covalent bond. Now, in the previous slide, I said that you can compare the relative polarities of different bonds by seeing which one has the greater electronegativity difference. So in our final example, we will rank the following bonds in order of decreasing polarity. Decreasing means big to small, so I'm going to rank these from the most polar to the least polar, okay, and we'll explain why. Well, I'm going to need to calculate the electronegativity differences for each of these bonds, so let's look up the values. Here they are for simplicity. Phosphorus 2.1, nitrogen 3.0, oxygen 3.5, fluorine 4.0. So for the PO bond, that's going to be 3.5 minus 2.1 equals 1.4. For the phosphorus fluorine bond, 4.0 minus 2.1 equals 1.9. And for the phosphorus nitrogen bond, 3.0 minus 2.1 equals 0.9. So here are my electronegativity differences. I can clearly see that the phosphorus fluorine bond with the largest difference in electronegativity values must be the most polar, followed by the phosphorus oxygen bond with an electronegativity difference of 1.4 is the second most polar, and finally the phosphorus nitrogen bond with an electronegativity difference of 0.9 is the least polar. In our next video, we'll talk about ionic bonding.